Activating the thermal batteries. 5, 4, all systems are go. We have main engine.
What we are looking at is the DAICHI-3 launch vehicle awaiting its first test flight with DAICHI-3 on board at this Tanegashima Space Center. The scheduled liftoff time is around 10:37 this morning. Good morning, everyone watching this live stream. It's been almost 3 weeks since the previous launch cancellation, and so we will be bringing you a live stream of the H3 launch vehicle launch with DAICHI-3 on board once again. My name is Kotomi Mimura, responsible for PR at the JAXA Tanegashima Space Center. Nice to meet you all. It's been 3 weeks. It's been a while. I will also be giving some technical explanation. My name is Isao Kotani, an engineer from JAXA. And the live stream today will be provided with simultaneous English interpretation, so please go to the site using the URL. As many of you may have seen in the previous live stream or the news, we attempted our first test flight of the H3 launch vehicle on the 17th last month. However, because the system detected an anomaly right after the first stage LE9 engine was ignited, it did not send the signal to fire up SRB-3, and hence the launch was cancelled. Starting on that same day, efforts were made into determining the cause and implementing countermeasures, and as a consequence, we have once again arrived at this launch date today. So to begin with, we'd like to explain about what caused the cancellation of the launch on the previous occasion. Kotani-san, over to you. So I'd like to give some easy-to-understand explanations. I have actually prepared something like this. This is 1/100th model of the H3 launch vehicle. But before I explain about the phenomenon, I'd like to start by explaining what a rocket is about, or launch vehicle is about. All the launch vehicles essentially have the same function, but right at the top we have a place called fairing. which is a payload fairing. And so the launch vehicle is a kind of a transportation unit to transport the satellites or the explorers located in the payload fairing. Large amount of the thrust is required, and so from here below is essentially the engine and the fuel. Right at bottom of our first stage, I don't know what you can see here. And this is where we have the LE9 engine, and it actually uses the liquid hydrogen and liquid oxygen as a fuel. And we have two of these, and adjacent to that, we have the SRB3, which is a rocket booster using solid fuel, and it generates significant amount of thrust. And the second stage, so up until here is our first stage, but this section at the top is the second stage. And hidden here is LE5B3, which is also an engine using liquid fuel. So that is how the launch vehicle is made up. And so this first stage, the engine and the rocket booster, these are utilized first to launch into the space. And the launch vehicle, it's not the case that it just goes up in the air when it is ignited, but we go through what we refer to as a launch sequence. So various preparation and procedure are required before we make the launch, and I'd like to give some explanation about that today. So if you can take a look here. And so this is quite a simplified version of what happens in the 480 seconds to the liftoff. So at 480 seconds before the liftoff, we start the countdown. And preparation proceeds at 240 seconds before liftoff. The language was lost, but before we enter into this mode, the Launch Control Center, and I'll explain about what this is about later on, but within the Launch Control Center, there is a Launch Commander, and this Launch Commander will make a final confirmation, give a permission to move into this mode. And there is kind of an instruction button that he presses to go into the automated countdown sequence. And so various preparation, they proceeds, and the flight mode is switched over, and the system is ready for launch 15 seconds before the liftoff. 6.3 seconds before the liftoff, LE9 engine is ignited, and it takes about 5.9 or 6 seconds for the engine to start up. And so we essentially wait for the engine to become stability, and then the SRB3 is fired up, and that will be followed by the liftoff. And so pressing the instruction button in practice means the start of automatic the countdown sequence with a person physically pressing the button. Yes, so it happens somewhat ahead of the actual liftoff. The sequence proceeds, and after the LE9 engine is ignited, it's just an instantaneous decision that leads to the liftoff. And what happened on the 17th of February is that after the LE9 engine was started up and the phenomenon occurred, and after the startup, these are the detailed procedure on this slide. So on the left is the normal the procedure that takes place for a launch, and what happened on the 17th is shown on the right. So after the LE9 engine is ignited, after confirming that it has stabilized, then the launch vehicle would judge and acknowledge that the conditions are met for the launch, and then provide the approval to ignite SRB3. And there is a safety device, and so this is essentially like releasing this safety mechanism. And then after this safety mechanism, then the ignition signal is sent for a liftoff. But on the 17th of February, the previous occasion, after the LE9 was started up, and gave the approval to ignite SRB3, but there is a vehicle controller, which is an important controller within the vehicle, and within this device, there is a instability in the electricity, and so the launch vehicle considered this to be an anomaly, and so despite the fact that LE9 engine had started up, it sent out a signal to cut off the engine, stopping the sequence. So that is essentially what happened the previous occasion. And so, after the approval for Ignite SRB3 to the cut off the LE9 engine, it all took place in 1/10 of a second, so not even a time to blink your eyes. This all occurred when the power supply was cut off from the ground facility to the vehicle, didn't it? That's right. And if you take a look at this photo here, until immediately before the launch, the launch vehicle is linked to the ground facility and the movable launcher, which the launch vehicle is standing on through an electrical system connector. And it's through this connector that electricity and communication is provided to the launch vehicle. Now, with regards to the first stage, it's hidden, so you can't see the connection, but there is a connection beneath the launch vehicle. But for the second stage, if you can look towards the top, you can see a sagging line, and this is what is providing electricity and also communication to second stage. And just before the liftoff, well, this is the vehicle controller. And this is an orangey type looking device. It's just before the LE9 engine, or just above the LE9 engine. And after LE9 engine is start up, and the ground facility, they actually electrically cut off the power to the launch vehicle. And at the bottom is the ground facility, and the vehicle controller. This is linked, and this line is actually cut off. And immediately this was cut off, then the vehicle controllers, the electrical system became unstable, and there is what is referred to as an integrated circuit switch. And so that switch was actually cut off, a semiconductor switch was cut off, and so it was a malfunction. And when that happens, and there is a battery within the launch vehicle, and towards the right, the engine control unit. And so there is a first stage battery to the engine control unit, so the electricity should have been supplied, but because of the instability in electricity, the switch was turned off, and so the electricity was cut off, and that was considered as an anomaly. And this switch for a power supply should have been on, but it was in the off position. And that was the reason why anomaly was detected, right? That's correct. Now, at that stage, LE9 engine was already active. Now, that wasn't a problem? Well, this is one feature of the launch vehicle, but of course there was no problem with engine because there is a backup power source. But not just with the engine, but the launch vehicle adopts a concept of fail-safe. Fail means a failure, but irrespective of whatever failure one experiences, the launch vehicle can be stopped safely. That is the concept used for design. So even with one failure, it's not a problem. So a safety designed to prevent secondary damage, in a sense, isn't it? That's correct. And so the countermeasures have been implemented. Yes, I forgot to talk about the countermeasures. Of course, I said the electrical instability, but why did this occur? When the power was cut off, the electricity becomes unstable, and this is technically referred to as a noise. So the current or voltage sometimes becomes larger or smaller, and that is stability. And this sometimes causes a switch that should not have turned off to turn off. So it's a malfunction. But we've implemented countermeasures to prevent the noise on this occasion. Thank you very much for your explanation. Now, we received many words of support and a lot of vigorous encouragement from many people from the day of the launch cancellation until today. All the people involved were very much inspired by these words of encouragement. Thank you very much for your words.
So let's turn our attention back to today's launch, due to happen soon. And what you see behind us is the DAICHI-3 launch vehicle at the launch site. You can see clearly. Yes, we're about 3 kilometers away at the Takesaki Observatory. And now it's at the launch pad. It's standing there. This time, finally, we have to see it go. We have to see it leave. And as for the weather today, same as the previous time, we have very clear weather today. And from the meteorological office, let's read some of the weather data. Today it's sunny. Northern wind, 3 meters per second, 18 degrees Celsius is expected. So in terms of weather, it seems that it's very good, and we have high pressure, and so no problem weather-wise. That's written in the report, so no concern there. So can you explain a bit about the weather conditions required? Well, I think we have good conditions, but just to be sure, we have to look at the wind, rain, cloud cover, and lightning. So we check until the last minute whether there are not any problems there. So today we have a maximum 5 meters wind, not a problem because the maximum is 20 meters. So there are various standards, criteria against which we check. Thank you very much. So weather is a very important condition for launch. So there is the LCC, the Launch Control Center, where various work is done remotely. And we have a camera feed from the LCC. So here the rocket's condition is constantly monitored, and fuel loading and the pre-launch checks are carried out remotely as the final launch preparations are made. The Launch Control Center is located 3 kilometers away from the launch pad. Why do we have to have that distance? Can you explain? As we explained, we use liquid oxygen and liquid hydrogen, which are dangerous. So in order to ensure safety, we say 3 kilometers. So any facility that has people in it has to be placed 3 kilometers away from the launch site. So to ensure safety of the operators, it's located 3 kilometers away. So what kind of work will be done in the Launch Control Center, the LCC? Well, the countdown sequence that I explained earlier, that work will be done mainly here. People sitting here, they are in charge of different parts, and so they're looking and confirming the condition of the rocket. And there is the launch conductor also sitting here. Seems everything is calm there. Yes, they're all sitting there, so it means that everything is good. So I want to explain today's broadcast schedule. So first, the overview of the H3 launch vehicle, the mission of the DAICHI-3 will be provided, and message of support from viewers and companies will be shown. Next, a video summarizing the history of the H3, the flight plan, and the flight sequence will be provided, and the launch is scheduled around 10:37. So today's mission, we have liftoff, and then SRP-3 separation, fairing separation, first, second stages separation, and then ALOS-3 separation at the end. So 40 minutes to launch. So let's introduce the H3 launch vehicle. So we did this last time. JAXA and Japanese companies consolidated their efforts to develop this new rocket. So after the launch of the test flight, it will go immediately into the commercial launch service, so launch business. And so private sector, which is Mitsubishi Heavy Industries, they have been taking part in the design process. If you go into business stage, you will be launching not just Japanese satellites, but satellites from the global market. So we have developed this H3 rocket, which can be competitive in the global market. And so I've already explained the structure. So let me talk about the size now. It's 63 meters length, and this one is 57 meters. There are 2 types of fairings. If you use the long version, it's 63. If you use the short version, it's 57. This time it's 57 meters. Diameter 5.2 meters, one size larger than the H2A. It's difficult to image how big it is. If it's at 57 meters, it's about the same size as the Leaning Tower of Pisa. Did you know? Oh, how about in Japan? Well, there's the Oarai Marine Tower. It's about the same height. That's 60 meters. So if you know the tower, you can see how large this is. So if you really look at this, you can actually sense the hugeness of it. It's a solid, big vehicle. So H2A and H2B rocket had the marking of Nippon on the side, but this time with the hope that the people all over the world will use this, it has been changed to Japan. I like the Nippon too, and we see the national team in sports, and I think it's good that we're appealing Japan. And this H2 representing Japan. So we've summarized the H3 rocket and its path to development. Please watch the video.
私たちが携わる宇宙開発は1957年に旧ソビエト連邦現在のロシアが世界初の人工衛星スプートニクを打ち上げて以来60年以上にわたり続いてきました。宇宙開発の目的は多岐にわたっており、例えば宇宙という未知の領域を研究し、宇宙や惑星の成り立ちや生命誕生の秘密を解き明かす知的探求心の解明が最もイメージしやすいかもしれません。さらに今や当たり前となった天気予報や道案内、自動運転など私たちの生活に欠かせないこれらのサービスの実現には宇宙開発による技術が使われていることを皆さんはご存知でしょうか。地上の暮らしをより便利にするために生み出された技術が発展を続け、宇宙開発と交わりお互いを高め合う。宇宙開発はもはや私たちの生活になくてはならないものになりつつあります。私たちの暮らしと密接に関わる宇宙開発に欠かせないのがさまざまなものを宇宙に輸送するロケットです。では世界中にロケットが多く存在する中でどうして国産のロケットを新たに作る必要があるのでしょうか。それは日本が独自にロケットを持ち続けることで生まれるメリットがたくさんあるからです。例えば先ほどのような私たちの生活を豊かにするサービスを実現するには日本が適切なタイミングで必要な人工衛星を自在に打ち上げれる環境が重要になります。それには日本独自のロケットが必要不可欠になるのです。H3 は現在運用中の H2A の後継機として今後20年間使い続けることを見据えた日本の新しいロケットになります。国内外問わず数多くの人工衛星を定期的に打ち上げることを目指し H3 を安定して使い続けることが目標となります。そのためには日本だけではなく世界中から選ばれるロケットを目指さなくてはいけません。H3 は3つの要素、打ち上げたい時に打ち上げられる柔軟性、これまでのロケット開発で培った高信頼性、低価格の実現を目指し誰もが宇宙空間を活用できる時代を目標に徹底した利用者目線で使いやすさを追求していきます。2014年のプロジェクト始動から8年、途中にはメインエンジンの技術課題を克服するために2度の開発計画の見直しもありました。開発を主導した岡田正史プロジェクトマネージャーは H3 をこう語ります。
ロケットっていうのは地上のすごく劇的な進化を宇宙から支えるための乗り物だと思うんですよね。H3 ロケットは構想から約10年のロケットです。打ち上げの成功がゴールではなくて我々はその打ち上げの成功が出発点だと思っているので早くこのロケットをデビューさせて世界中の方々から使っていただけるようなものにしたいと思っています。
さまざまな困難を乗り越えついに完成した H3 ロケット。試験機1号機の打ち上げはすぐそこまで迫っています。新たなるフロンティアへ未来を背負った H3 が間もなく飛び立ちます。日本の技術で宇宙輸送をリードせよ。 H3 ロケットのメインエンジンとして搭載されるのが今回新たに開発した LE9 になります。これまで日本が培ってきたロケットエンジン技術を集結するとともに新たな技術にも挑戦し H3 が目指す柔軟性、高信頼性、低価格を高いレベルで実現することを目指しました。エンジンの燃料に液体水素、酸化剤に液体酸素を使い、搭載する人工衛星の重さや投入する軌道に合わせて LE9 エンジンを2機ないしは3機を束ねてロケットに装着します。 LE9 は H2A のメインエンジン LE7A と比べ推力が約 1.4 倍にパワーアップしたことで固体ロケットブースターなしで衛星を打ち上げることが可能となりました。また重い人工衛星を打ち上げる場合には固体ロケットブースターをつけるなど従来の H2A や H2B に比べて幅広い打ち上げが可能となります。このパワーの大きいエンジンを安くかつ信頼性を高く実現するためこれまでのロケット開発で得た経験と新しい技術をバランスよく取り入れました。その中でも特徴的なものを3つほど紹介します。まず LE9 で採用するエンジンの燃焼方式は従来のものよりシンプルな仕組みにすることでより高い安全性を実現しました。またエンジン全体の部品点数を減らすことができこれにより高信頼性と低価格を高いレベルで両立することが可能となります。次に LE9 には 3D プリンターで製造した部品がいくつも使われています。今までロケットエンジンには形が複雑で溶接やボルトを使った部品がたくさんありました。これらを 3D プリンターで一体成形することで大幅な部品点数削減、コスト削減を実現しました。そして電動バルブの採用でいろいろな作動範囲で燃焼することができるようになります。これにより燃焼試験の回数を大幅に削減することができました。このような最新の技術の粋を集めた LE9 エンジンがたどってきた道のりは決して平坦なものではありませんでした。 JAXA では2005年から約10年間技術実証を目的とした LEX エンジンの開発を行い2014年から LE9 エンジンの開発が本格的に始まったのです。開発の段階ではさまざまな技術面での問題が発生しました。その一つ一つの壁に向き合い生じた技術的課題を確実に解決するためにそして今後20年使い続けることができるロケットエンジンに仕上げるために2度にわたり試験機1号機の打ち上げ計画を見直しました。
この LE9 エンジンは2002年から研究が始まってですので、ほぼ20年ぐらいの時間をかけて開発してきたエンジンになります。でもこの技術というのは、結構厳格で、我々開発陣の願いとか希望といったものというのは、なかなか通用しない、思い通りにならないということが、結構ありました。ある意味残酷な現実というものを突きつけられているという部分があります。ただ最後ですね、何としてもこの世界初のエンジンを開発させてやるんだという関係者の皆様、これは我々 JAXA だけじゃなくてメーカーの方とか部品のベンダーの方も含めた強い思い、そういったものが実を結んでこのエンジンの完成にこぎつけることができたというふうに思っています。LE9 エンジンの開発担当者として一点の曇りもなく自信を持って H3 ロケットの初号機に使えるエンジンを仕上げることができたというのは万感の思いです。
So more than a decade, we took quite a long time to develop the H3 launch vehicle. Kotani-san, you were involved in the concept for H3 launch vehicle. That's right, more than 10 years ago. So in a team to consider a concept, we had a lot of discussion as to what type of launch vehicle we were going to develop. But after it became a project until now, and so Okada project manager and others, they were saying there were a lot of, the ups and downs. And of course, the development procedure was certainly not that easy. So because I know that, and the state today, we're awaiting the launch, is something that is quite a moving situation for me. I feel, so happy that we have arrived at this day today, although it's the second time. We are now at 9 minutes past 10, so we have 28 minutes to go before liftoff. And so I'd like to recap the relationship between the launch vehicle and the satellite. Kotani-san, please. Well, as I have explained at the outset, the launch vehicle is a transportation device. It is a transportation device to deliver the satellite on the top. So it's like a delivery service. Well, that is a super fast delivery service, isn't it? Yes, the Daichi will be delivered to the destination in 70 minutes. So it's super fast. But you need to travel at 8 kilometers per second in order to escape the gravity of the Earth. So there is a lot of fuel. In fact, about 90% of the weight is fuel. Did you know? Yes. So essentially, you can tell by the look that it is made of a fuel tank. So the orange portion is the insulator around the fuel tank. And so essentially, the entire launch vehicle is the fuel tank, isn't it? Thank you. So next, could you explain about the types of satellites? Yes, there are many types of satellites. We have the communication satellite, the meteorological satellite, or science satellite. But on this occasion, we'll be launching Earth observation satellite, which is dedicated observing the Earth, detecting the light from the sun. It's like they're taking photography, and also sends out the electric the radio waves, so you have lidars to make various detection. But on this occasion, we'll be sending up the Earth observation satellite. So thank you. And we have a movie to introduce the Daichi-3 satellite to be launched, and also interview with Mr. Yonisaka, General Manager.
日々変化する大地の表情を捉え、私たちの社会に役立てる大地の目。大地3号は大地の光学ミッションを引き継ぐ地球観測衛星です。大地からさらに大型化、高性能化した光学センサーを搭載しており、大地の観測幅 70km を維持しながら地上分解能をおよそ3倍向上させ 80cm を実現。より鮮明な画像が得られます。大地3号は衛星直下の地表面を日々観測し、データを蓄積し続け、年や季節などによる地表面の変化を捉えます。アーカイブされた観測データは世界の高精度な地理空間情報の整備と更新に貢献します。災害発生時には被災地を迅速に観測、多種多様な災害に対応するために複数の観測モードを有し、衛星直下以外の任意のエリアも観測できます。観測されたデータは速やかに地上へ、被災前後のデータを比較し、建物の倒壊や道路の寸断など詳細な被害状況を把握します。地球を見守る大地の目。大地3号は地球の安全と安心のために、そして豊かな社会のために宇宙へ飛び立ちます。
2015年にプロジェクトが開始してから設計・製造を行ってきて、昨年10月に製造が完了し種子島に運んだというところでございます。大企業から下町の小さな工場までいろいろなところの会社さんが関わっているので、正確な人数は分かりませんけれども、だいたい30社以上の方々が関わっていただいております。まずは皆さんにこの映像を見ていただきたいと思っておりますと同時に、自分もぜひ見てみたいと思っております。
Tani-san, what did you think? Well, the resolution from the first generation to the third generation of Daichi, there's been significant improvement in resolution. So 80 centimeters of resolution, and which is like the number of pixels on a digital camera. So 80 centimeters. So that's from a space you'll be able to recognize cars. That's the kind of resolution that we're talking about here. And so from Daichi-1 to Daichi-3, it's essentially like the TVs are becoming high vision to 4K. I don't know if you can imagine this, but that's the kind of evolution that we're seeing here. That's a great evolution, isn't it? But because the imagery will be based on high resolution, the amount of data is going to be quite significant, so it's going to be an issue to send that to the ground. Yes, the satellite down to the ground station. So there is an antenna. There is a ground station with an antenna that communicates with the satellite, and so the data can be sent or received when it actually flies over the ground station. But when there is the large amount of data cannot be sent in a timely manner. So that is one challenge that we need to accommodate. So as part of this solution is the laser utilizing communication system. Mr. Yamaka, our project manager of this system operation, will now introduce the technology for data transmission to be used for Earth observation satellites.
地上から見て常に同じ方向に見える静止軌道衛星光データ中継衛星を用いてユーザー衛星と呼ばれる地球観測衛星などより低い軌道を飛行する衛星との通信を中継するシステムです。データ中継衛星を用いた通信システムはユーザー衛星と光データ中継衛星の間、光データ中継衛星と地上の間の2つの通信回線から構成されますが、そのうち前者の方の通信回線を光通信化したものがルーカスの大きな特徴でございます。データ中継システム自身がメリットを持ってまして、広い通信範囲が可能ということでございまして、トータルで送れる通信量が大きくなること、あとその広い範囲に対してどこでもコマンドを打つことが可能ですので、利用範囲が広がることが期待できます。さらに光データ中継衛星化することにより光のメリットである高速交代規制とか、またアンテナを小さくできるために機器自体を小さくすることが可能になります。宇宙光通信、とりわけ技術的難易度の高い衛星間通信という観点では JAXA は欧州の宇宙機関と並び世界のフロントラインに立って軌道上実証を含む研究開発を進めてまいりました。その集大成として、実用に供しうるレベルの光衛星間通信を実証できることがルーカス開発担当としては非常に大きな喜びでございます。加えて特に今回第1、3号により得られる素晴らしい観測画像の伝送になり、観測データが広く皆様のお役に立てるそのプロセスの一環として寄与できることを光栄に感じております。
So that we watched the VTR about the communication system. What did you think? And so this concept has been around, but using optical communication shows that technology has evolved. So huge amounts of data, sending that on a timely basis. How does that help our lives is the issue that I want to learn more about. Okay, then let's ask the people involved in data usage of Daichi-3, how the data is provided, how they're expected to be used. Please watch this video.
PASCO は航空写真測量の会社として創業し、今年10月で70年を迎えますが、今では航空機以外にも人工衛星、車両、ドローン等により得られるセンシングデータから地理空間情報を収集し、社会課題や経営課題に対するソリューションを提供しています。PASCO は地上運用システムの整備、衛星運用、そしてデータ配布事業を JAXA さんの共同事業者として担います。またデータが広く普及するよう利用事例作りを進めてまいります。第3号のデータは地図データの整備、災害対策、スマートシティやスマート農林水産業並びに環境監視等広い分野での利用が期待されております。第3号で観測したデータは見てみるという PASCO のウェブプラットフォームから入手することができます。見てみるでは利用者は 監視エリアや観測期間を設定するだけで簡単に衛星データの検索閲覧をすることができ、続いて処理仕様を指定することでオーダーを行うことができます。第一3号から得られる高品質で利用用途の広いデータは、衛星データ利用の市場をより一層ダイナミックなものへと変貌させていくと確信しており、私たちがその一役を担うことを楽しみにしています。衛星データが多方面で使われるよう JAXA さんやパートナー企業とともに取り組んでまいります。
土砂災害研究部では豪雨や地震、火山噴火などに起因する土砂災害の被害を防止・軽減するため、土砂災害のメカニズムや対策施設の効果的な整備、警戒避難や監視対策などソフト対策に関する研究を行っています。土砂災害は山岳地や丘陵地で発生することが多く、まずどの場所でどのような種類や規模の土砂災害が発生したのかを把握するために第一3号のデータを使用する予定です。土砂災害分野で特に変わる点としては、やはり災害発生後の初動として重要な被害状況の迅速な把握が可能となることが大きな変化と思っています。近年では気候変動の影響や大規模地震の切迫性が指摘されており、土砂災害の頻発化や激甚化が懸念されているところです。防災・減災、国土強靭化は国を挙げて進めており、第一3号の打ち上げが成功して観測を順調に開始し、災害時には大いに活用されることを期待します。
地図の作成や更新のための技術開発を担う部署です。その一環で衛星データを利用し、効率的に地図を更新するための技術開発を行っています。国土地理院が整備している電子国土基本図の更新に第一3号が撮影した画像データを使用する予定です。電子国土基本図はさまざまな地図の基礎となる我が国の基本図で、2021年9月に施行されたデジタル社会形成基本法において、公的基礎情報データベースという正確性や最新性が確保された社会の基盤となるデータベースの一つに位置づけられています。大きく4つのステップがあります。ステップ1は測量用航空機による空中写真撮影。次のステップ2が図鑑、地図を描く工程です。ステップ3が現地調査。最後が編集で、図化したデータに市町村名などの中期に関する情報を加えて作業が完成します。第一3号の解像度は初号機の 2.5 メートルから 0.8 メートルに向上しています。分解能が向上し、判読できる地物が増えることは地図の精度向上に直結します。今回第一3号のシミュレーション画像を25000レベルの電子国土基本図で利用可能か評価したところ、海、河川、湖の縁となる水害線や道路、鉄道、建物、植生、土地利用といった基本的な地物についておおむね問題なく判読可能であることを確認しており、ステップ1に加え電子国土基本図の図鑑にも利用できると期待を寄せています。また第一3号のデータから都市開発などで大きく変化している箇所を自動的に抽出し、電子国土基本図の更新すべきエリアを効率的に選定できるような技術開発にも着手したいと考えています。地図作成に携わる我々にとって待望の打ち上げです。第一3号から国土の様子を捉えた画像が届くのを楽しみにしています。
So many people are looking forward to the data from DAICHI-3, myself included. Now, this time, we solicited messages of support for the H3 launch vehicle and DAICHI-3. They were pasted on the SRB-3. So after the cancellation, we had the recycling, and we returned to the assembly building, and we saw the messages. At the time, there was anxiety and pressure. I'm sure that the operators were faced with such anxiety and pressure, but I think this really encouraged them. And many companies and organizations participating as supporters, and through the website and through events, they have provided messages of support. Thank you so much. We're very thankful. So your messages of support is going to fly into space. So H3 rocket and the ALOS 3 journey to date is now in a video. Please watch. So watching this, we see that a lot of work and testing have been carried out. The process is similar to that of the H2A and H2B rockets. The work is almost the same, but it's a very large rocket. And so in terms of the clearance, putting it in a narrow space was quite a difficult task. And this was when the launch vehicle was transported. We were walking alongside it, yes, under the rocket. And the rocket is overwhelming, but the launcher, the movable launcher, I really like it. It's very huge. And the rocket, even before fuel is injected, it's a huge, heavy thing. And so I was impressed by the strength of the dollies. More than 400 tons without fuel. And so the heavier ones, heavier configuration would be 1,500 tons. So that's about 1,000 cars, and the two dollies can lift that. So it's a very powerful thing. And we see that the operators waiting at the launch pad. So as soon as the rocket arrives, they start to connect the piping. And I was watching that, and I thought that was really cool. They're really waiting for the launch vehicle to arrive. And it's a difficult task, and there could be a slight misalignment. And of course, they can connect even with that. And we saw a lot of teamwork there. So let's look at the flight plan and flight sequence.
種子島宇宙センターから打ち上げられる H3 ロケット試験機1号機。ここからはそのフライトシーケンスを紹介します。およそ1分56秒後、SRB3 が分離します。そして3分34秒後、フェアリングを分離します。5分5秒後には第1弾、第2弾が分離。そして5分17秒後に第2弾エンジン燃焼を開始します。その後もロケットは飛行を続け、打ち上げからおよそ16分43秒後に ALOS-3 が分離される予定です。衛星分離後、第2弾はインド洋上へ制御落下を行います。
So let's look at the launch control center, how it is there. So what's the situation there? Seems everyone is calm, working on their respective tasks calmly. Yes. And we also have a link to the range control center RCC. So RCC remotely controls each of the tracking stations, monitoring the status of the flying rocket. It also coordinates with the LCC and conducts the whole launch operation from here. So the LCC, the Launch Control Center, oversees the preparation to launch, and so fuel injection and the countdown. And this RCC is in charge from the moment of launch, tracking the rocket. So slightly different roles between these two centers. So the data from the various tracking stations are collected here. Yes, we have the tracking stations along the path of the flight, so they are moved and the data is collected here at the RCC. So LCC is in charge up until the launch. Of course, they continue to monitor after the launch as well, but it's like they pass the baton to the RCC after the liftoff. Thank you. H3 launch vehicle launch is approaching. From here, let's watch the live video from the launch pad and the live voice coverage from the Range Control Center. It's now coming. It's soon. Let's watch.
480打ち上げ8分前です。現在各艇ともロケット打ち上げの最終作業を行っています。また警戒区域の安全は確認されています。
It's 8 minutes to launch. All systems are now in their final operations. The restricted area has been vacated and cleared.
450 440 430 420安全系準備完了。
Range safety system is go.
車上系準備完了。
Range system is go.
408、407、406、405、404、403、402、401、400。 390 380 370 360打ち上げ6分前です。現在車上の天候は晴れ、気温摂氏18度、北の風毎秒3メートルです。
It's 6 minutes to launch. The current weather at the launch site is fine. Temperature is 18 degrees Celsius. Wind is 3 meters per second from the north. The weather is still a go, and currently there is no constraint for launch.
本日の打ち上げ予定時刻は日本時間の午前10時37分55秒です。
Today's scheduled liftoff time is 10:37:55 seconds a.m. Japan Standard Time.
310、309、308、307、306、305、304、303、302、301、300、99、90、打ち上げ5分前です。
It's 5 minutes to launch.
95、94、衛星系準備完了。
Satellite system is go.
290、89、88、87、86、85、84、83、82、81、280、79、78、77、76、75、74、73、72、
71、270、69、68、67、66、65、64、63、62、61、260、59、58、57、56、55、54、53、52、51、250、49、48、47、46、45、44、43、42、41、240、39、
自動カウントダウンシーケンス開始。
Automatic countdown sequence has been initiated.
現在ロケットの管制は滝崎発射管制塔から行われています。
A3 is now operated under the command of Takesaki Launch Control Center.
22、21、220、19、18、17、16、15、14、13、12、11、210、209、208、207、206、
2段液体水素地上与圧開始。
Pressurization process of second stage liquid hydrogen has been initiated.
97、96、95、94、93、92、91、190、89、88、87、86、85、84、83、82、81、180、
打ち上げ3分前です。
3 minutes to launch.
76、75、74、73、72、71、170、69、
1段液体酸素液体水素地上与圧開始。
Pressurization of first stage liquid oxygen and hydrogen has been initiated.
機体の電源が外部から内部に切り替えられました。
The power has been switched to the internal systems.
52、51、150、49、48、47、46、45、44、43、42、41、140、39、38、37、36、35、34、33、32、31、130、29、28、27、26、25、24、23、22、21、120、19、18、17、16、15、14、13、12、11、110、109、108、107、106、105、104、103、102、101、100、99、98、97、
2段液体酸素地上与圧開始。
Pressurization of second stage liquid oxygen has been initiated.
89、88、87、86、85、84、83、82、81、80、79、78、77、76、75、74、73、72、71、70、69、68、67、66、65、64、63、62、61、60、
打ち上げ1分前です。
1 minute to launch.
55、54、53、52、51、
フレームデフレクター冷却開始。
Flame deflector cooling is initiated.
46、45、44、43、42、41、40、39、38、37、36、35、34、33、
ウォーターカーテン散水開始。
Sound suppression water system at the launch deck is activated.
27、26、25、24、23、22、21、20、19、18、17、16、15、14、
フライトモードオン。
Flight mode on.
12、11、10、9、
加工品トーチ点火。
Hydrogen purge igniter on.
全システム準備完了。
All systems go for launch.
メインエンジンスタート。
Main engine start.
SRB3 点火リフトオフ。
Solid boosters ignition and lift off.
第一3号を搭載した H3 ロケット天気1号機は2023年3月7日午前10時37分55秒に 種子島宇宙センターから打ち上げられました。
We have a successful liftoff for A3 launch vehicle test flight with 803 from JAXA Tanegashima Space Center at 10:37:55 seconds a.m. on March 7th, 2023, Japan Standard Time.
打ち上げ以降、ロケットの管制は竹崎発射管制塔から竹崎総合司令塔に引き継がれています。
The operation control of A3 has been switched from launch control center to range control center.
ロケットは現在、東南東方向の太平洋上へ飛行しています。
A3 is flying over Pacific Ocean to the east-southeast.
打ち上げ後1分が経過しました。
It's 1 minute into flight.
ロケットは正常に飛行中、地上局のロケット追尾状況も正常。
The A3 flight is on course and the ground stations are tracking the launch vehicle and all is good.
85、87、89、91、93、95、97、99、101、103、105、107、
SRB3 燃焼終了。
Solid boosters burnt out.
11、13、15、17、19、
SRB3 分離。
Solid boosters separation.
ロケットは現在、種子島内之浦の地上局から追尾されています。
Currently, Tanegashima and Uchinoura ground stations are tracking A3.
第1段エンジンの燃焼は正常、制御系飛行経路も正常。
The combustion of the first stage engine, altitude control, and trajectory are all nominal.
ロケットは順調に飛行を続けており、現在の高度は約 84km、秒速約 1.6km です。
The A3 flight is on course. Current altitude is about 84 kilometers. Velocity is about 1.6 kilometers per second.
はい、H3 ロケット試験機1号機。
So we have been able to see a successful launch of the H3 launch vehicle thus far. And what you are seeing right now is based on the information that we have received from launch vehicle replicated in CG, almost real time. And so the flight indicator for public, which we call the FIP. And it's looking at the direction that the launch vehicle is traveling at and also showing the height. And it is indicated as a line. And the data obtained from the launch vehicle is actually reflected into this. So it's showing the trajectory of the launch vehicle. So the satellite fairing separation has been confirmed. And what you can see is on the screen is X+, which is the time lapse from the launch.
ロケットは順調に飛行を続けており、現在の高度は約 175km、秒速約 2.4km です。
The A3 flight is on course. Current altitude is about 175 kilometers. Velocity is about 2.4 kilometers per second.
はい、この左上の方に。
And towards top left, you can see the altitude and the velocity. So we're traveling at more than 200 kilometers above underground. And on the left is the speed per hour. So what that's so it was accelerate to 28,900 kilometers an hour eventually. And so we are almost at the completion of ignition of first stage engine now.
第1段エンジン燃焼停止。
First stage engines cut off.
第1弾、第2弾分離。
First and second stage separation.
And so this second stage engine should ignition, but we're not heard the ignition start announcement as yet. But at ignition at 16 minutes 36 seconds, it will continue to ignite to take the satellite into the orbit. So we have seen the launch of the H3 launch vehicle, test flight #1. So that in itself has, I suppose, made me feel reassured. So we can no longer see it in the sky. So because of the fine weather, that we were able to see it quite high into the sky. We were able to see the SRB3 separation, but the launch vehicle is a delivery service, so we must separate the satellite. Otherwise, we will not be able to call the entire mission a success. So at this point in time, we still cannot be reassured as yet. And the people in RCC is keeping a close watch on the launch vehicle flight. As we discussed at the RCC, at the tracking stations, is actually tracking the launch vehicle, obtaining data from it, and obtaining locational information to confirm the current position of the trajectory. So let's confirm the trajectory as was explained, and this is reflecting the current flight data reflected in CG almost on a real-time basis. And what will occur after this is if the second stage is ignited well, then it will be separation of the satellites. So until 16 minutes past the liftoff, we will deliver the satellite to the delivery point. So the elevation is about 540 kilometers right now. And the target elevation is 675 kilometers. And so it seems that it is traveling at the needed the height, but looks like the velocity is coming down. It's coming down less than 10,000 kilometers an hour. I don't know whether this data is correct or not, but it seems that the velocity is coming down, and that is what we are able to confirm on the FIB. But is this the actual data, or is it based on the system? We need to check.
現在2段の点火が確認されておりません。引き続き状況を確認中です。
This is an announcement from the Takesaki Range Control Center to all launch operators and personnel. The second stage engine ignition has not been confirmed yet. We continue to confirm the situation.
繰り返します。現在2段の点火が確認されておりません。引き続き状況を確認中です。
The second stage engine ignition has not been confirmed yet. We continue to confirm the situation.
So we have not been able to confirm the ignition of the second stage engine. Well, on this FIP or on this CG, the signal for ignition of stage 2 has not come in, and so the elevation is at 625 kilometers, but the velocity is coming down. But is this the actual situation? We would like to await for updated information. We are confirming the situation right now, and so if you could bear with us, as soon as we receive updated information, we will convey that to you.
企画管理主任より打ち上げ作業関係者に連絡します。現在、第2段エンジンの着火が確認されておりません。引き続き状況を確認中です。
This is an announcement from the Takesaki Range Control Center to all launch operators and personnel. The second stage engine ignition has not been confirmed yet. We continue to confirm the situation.
繰り返します。現在、第2段エンジンの着火が確認されておりません。引き続き状況を確認中です。
The second stage engine ignition has not been confirmed yet. We continue to confirm the situation.
はい、今放送がありましたが、
So as was announced, ignition of the second stage has not been confirmed. The situation is being checked and confirmed. To repeat, second stage ignition has not been confirmed, so the situation is being confirmed. From where we are, we cannot see, so all we can do is wait for information to come in. But we're watching the CG and we're talking over it. The separation of first and second stage, we were seeing that the signal was sent, but the second stage ignition start, we did not hear. Give us a minute.
達成する見込みがないとの判断から指令破壊信号を送信しました。
今放送が入ってます。ちょっとお待ちください。
Destruct command has been transmitted to A3 because there was no possibility of achieving the mission. We are confirming the situation.
繰り返します。ロケットはミッションを達成する見込みがないとの判断から指令破壊信号を送信しました。
Destruct command has been transmitted to A3 because there was no possibility of achieving the mission. We are confirming the situation.
企画管理主任より打ち上げ作業関係者に連絡します。状況については分かり次第打ち上げ関係者に別途連絡いたします。これをもちまして本日の H3 ロケット試験機1号機の打ち上げ実況放送を終了します。
The status of A3 launch vehicle number 1 will be announced to all launch operators as soon as it will be confirmed. We are ending today's launch status report.
繰り返します。状況については分かり次第打ち上げ関係者に別途連絡いたします。これをもちまして本日の H3 ロケット試験機1号機の打ち上げ実況放送を終了します。
The status of A3 launch vehicle number 1 will be announced to all launch operators as soon as it will be confirmed. We are ending today's launch status report.
大丈夫です。はい、今放送が入り
As was just announced,
ロケットはミッションを成功する
rocket could not complete its mission, so destruct command was sent. it was decided that the rocket could not complete its mission, so destruct command was sent. Destruct command is we send the signal, and there is this device that is activated to destruct the rocket. And then it will not fly any further and it will come back down to Earth. So we were watching in the CG. First stage combustion was completed, and we could see that command was sent to separate the first and second stage. 5 minutes 27 seconds. The second stage engine was started to ignite, but in the CG that signal was not received. We were not able to confirm that. So what happened there? Something that we have to investigate, looking at all the data. So during this broadcast, it will probably be difficult to explain in detail all the phenomena. So please, we'd like to communicate to you through the website or through other media. So we cannot expect more news to come in. And so we would like to conclude the live broadcast for the DAICHI-3 first test flight. Very regrettable this happened. It's a test vehicle, so there were various challenges, and there were some risks, of course, because it was newly developed. So going forward, we're going to investigate the cause. Yes, we need to identify the cause and then reflect it in the next test vehicle. That would be our mission. So as for the detailed information, please visit the JAXA website. Information will be provided there. Thank you for watching the live broadcast. Thank you very much.